Hi guys, in this video we're going to do another DC analysis of another common emitter transistor amplifier with a slightly different configuration than the ones we saw earlier. Alright, okay, so this is the circuit that we are going to analyze, and notice that this node here is labeled as VC for the collector terminal. Alright, so this is our NPN transistor. Okay, so in this question, we're asked to figure out what IC and IBs are, yeah, and what RB should be. If you notice here, RB is not labeled with any values. Given that VC is 60% of VCC, well, VCC is 10 volts, so 60% of VCC means obviously 6 volts. So VC is 6 volts. All right, and since VC is 6 volts, and since VE is 0 volts, so VC is going to be equal to VCE, right? So it's the voltage drop across from collector to emitter. So VC also happens to be VCE. All right, so as usual, let's label our currents and voltages. All right, so first let's do the current. All right, so we have this. That's going to be our IB, and this is going to be our IC, and of course this is our IE. Okay. Now notice the fact that the current from this VCC is going to split between IB, that's going there, and IC. So there's only one power source in this particular configuration. All right. In terms of the voltages, so we have a few here. So for example, here, obviously VCC is pointing up. All right. So VCC is pointing up, and since IC is going down, so VRC is actually going up, pointing up rather. So positive VRC, that is. And since IB is moving from left to right, and therefore positive VRB is actually in this direction. All right, so again, this is an NPN transistor, so VBE is pointing that way, right? So that's VBE. All right, let's talk about VCE. That's VCE here. So VCE is obviously going to be in this direction. All right, so that's VCE. And to complete our VCB part, all right, so VCB part, so the collector is going to be, because this is NPN and it needs to be reverse bias. Yeah, remember that? It needs to be reverse bias for a amplifier operation mode or forward active mode for the NPN transistor. So VCB is going to be in this direction, right? So that's VC positive in that direction. All right, okay, so we have two loops here, right? So we have a loop that is here and a loop that is over here. All right, so for us to work out what the value of RB should be, well, using Ohm's law, see if you want to know what R is, from Ohm's law is V equals IR. So for us to work out what R is, we need to know what the V is and also what the I is. So V means the voltage of RB, I means IB. All right. All right, so how do we do this? All right, so one way we could do is we could work out the various values for. So we just start with the condition first. So let's for example do a left loop equation. All right, so the left loop equation, referring to this side here. All right, so the left loop equation, if you notice, there is a 10 volt at the very top here, right? So this is 10 volts, so that this entire node is 10 volts, all right? So the entire node is 10 volts. So this is 10 volts, that's VCC, right? And then you have VBE. So you actually have this equation. You have VCC, right? So you have VCC is equal to VRB plus VBE, all right? So VCC is equal to VRB plus VBE. And we kind of know everything except for VRB, so we can work that out. All right, so therefore we can say VRB is equal to VCC minus VBE. All right, so that's 10 minus 0.7 volts, so that's equal to 9.3 volts. So we know what VRB is. All right, okay, so the current, for us to work out what RB should be, we need to know what the current is. Well, we don't know what it is. We don't have any ICs. We don't have any. We have beta, but we don't have IC. So we need to work out IC first. All right. So IC is over here. So it will affect the voltage drop across RC. So let's work out the loop equation for this side. All right. So write loop equation. All right, so we have VCC, we have VRC, and we have VCE. So that's VCC is equal to VRC plus VCE. All right. Okay. Now we saw earlier in the question it says that assume that VC is at 60% of VCC. So we can actually figure out what VCE is, because VCE is actually equal to VC, right? So this is equal to VRC plus VC. And VC is equal to 60% of VCC. So we kind of know everything. So we can actually work out what VRC is. All right. So therefore, so VRC. Okay. So so VRC plus 60% or 0.6 times VCC. Right? All right. So that's what VCC is equal to. So then we can actually work out what VRC is. So VRC, all right, so VRC is equal to VCC minus the 0.6 times VCC, right? Which is equals to 10 minus 6. So therefore it's 4 volts. So we know that VRC is 4 volts. And since we know what value of RC is, that's 400 ohms, so we can actually work out what IC is, right? So let's do that. Okay, so the next stage is, because we know what VRC is, so therefore VRC, according to Ohm's law, is also equals to V equals IR, so IC times RC, all right? Okay, so the only unknown is just IC, so therefore we just say IC is therefore equal to VRC divided by RC, right? So that's 4 divided by 4 volts divided by 400 ohm, right? So 4 volts divided by 400 ohms, so 4 divided by 100, we got 0.01, so that's 10 milliamps. All right, so we got 10 milliamps. So now we have IC. Okay, so well, since we have IC, we can therefore work out what IB is. All right, through the beta relationship. So we can use that. So we can say IB, all right, is equal to IC divided by beta. Okay, so that's 10 milliamps divided by 100. Okay. So now we have IB is equal to 100 microamps. All right. So we have IB. Since we have IB, we can actually work out what RB is, because we know that RB through Ohm's law is simply V over I. So V is VRB divided by IB. All right. So VRB is 9.3 volts divided by IB, which is 100 microamps. All right. So you'll get an answer of 9.3 divided by 100 E 6. So that's 100 microamps equals 93 kilo ohm. 93 kilo. All right, and that's the answer. Okay, so see you guys in the next video.